Welcome to part 2 of Energy in the Ecosystem, Chapter 3. Today we're going to be looking at energy transfer in the ecosystem and how to measure that transfer. So, first thing we're going to look at is just a lateral transfer and how energy first gets into the ecosystem, again through photosynthesis, into the producer. The producer grows and develops, metabolizes. As you can see here, heat energy is dispersed through this metabolism process. And then anything that's left over is utilized by the herbivore. In this case, we have a herbivore being a caterpillar. The caterpillar eats and gets fuel from the leaves, and then as it metabolizes and grows, it's going to give off heat as well. So there's a loss of energy. Remember, the second law of thermodynamics is loss of energy to heat and becoming very disorganized energy that can no longer do work. So the worm or the caterpillar, then that energy that's left over in the caterpillar is transferred to the bird. And in this scenario, it is the top of our food chain. Again, we're going in a lateral direction, so we're going from one plant to one herbivore to the carnivore, or the secondary consumer. And then, of course, as if the bird dies, then we have decomposers, or the plant dies or the worm dies before the bird gets it. We have decomposers that actually start breaking up that dead matter and returning it as nutrients to the soil. So there's also an energy exchange there as well as a heat exchange. Food chains usually are 3 to 5 levels, trophic levels, and that's because there is a loss of 90% of the energy at each trophic level. Okay. First level is always producers. Second level is always going to be your primary consumer, and this is where you can get tripped up, because trophic levels, you have 1, 2, 3, 4. When you have a primary consumer in your second trophic level, sometimes that can trip you up with trophic levels, because you've always got to remember that your first trophic level is your producer. And then we move on to the consumers. Primary, secondary at the third trophic level, and tertiary at the fourth trophic level. Then eating at all levels are your decomposers. Now, in a terrestrial ecosystem, you're only going to get 3, maybe 4 levels of movement. Very rarely will you see a fourth or quaternary consumer. Sometimes you will see that, but very rarely. That is more applicable to an aquatic ecosystem, because an aquatic ecosystem excuse me, holds more energy. There's more producer growth in an aquatic ecosystem with the algae. Food webs are a more complete view of the energy transfer. Normally, organisms do not feed or gain energy off of one other organism. They offer a variety of food sources, just like you. You don't just eat carrots. You don't eat just hamburgers. You eat a well-balanced meal, or hopefully you do. And organisms in an ecosystem, they eat more than one other organism as well. If they didn't do that, sorry about that, then they are called specialists if they only eat one thing. And in a terrestrial ecosystem, in most ecosystems, not even terrestrial, ocean as well, if they only have one food source, if something happens to that food source, that specialist is very prone to extinction, and it sets it up. for that. Now, specialists can survive in the tropical rainforest. There are quite a few specialists, in fact, in the tropical rainforest. And that's because it has a very, very high level of producer productivity, more so than any other terrestrial ecosystem. Okay, so what we're looking at here are different feeding patterns. So let's start at the top where we see the lion. The lion has an extremely varied diet, and the arrows that are pointing to the lion means that that's where energy is coming from. The lion is getting energy from the gazelle, the zebra, the wildebeest, and the giraffe. So he has, in this scenario, in this food web, he is actually getting energy from all four of these. So if one of them, say the gazelle, became extinct, do you really think that the lion populations would suffer to the point of extinction? Probably not. They would probably start feeding more heavily on the other three. So those populations would probably decline somewhat. But not enough to where it would matter, because not only the gazelle is gone, that is true, but the rest of these guys now have more feeding ground. So they're going to be able to reproduce at higher levels, even though the lion is eating them at higher levels. So it could be a wash. Now, if the lion lost 2 of his 3 sources of food, that will make a difference, because now he only has 2 sources of food, and chances are he'll be eating those at a much, much faster rate than they can reproduce. So let's look at this now in the sense of the food chain. Okay, starting with the grass. Looking for the exchange from grass to gazelle to lion. That is a food chain with basically 2 exchanges. The gazelle eats the grass and the lion eats the gazelle. Let's look at the food chain from the grass to the hare to the cheetah. Cheetah doesn't only eat the hare, does it? It also eats a gazelle. So we can make a food chain from the grass to the gazelle to the cheetah. So a varied diet for the cheetah as well as for the lion. What we're looking at are different food chains, and basically this is a transfer of energy. Okay. Just, you need to know these words. Autotroph is the equivalent of a producer. Those are plants. They're going to be the ones that at the base of the food chain. Heterotrophs are consumers, and they can't make their own energy, so they have to consume it. Primary heterotrophs or primary consumers are herbivores. They only eat plants. Secondary are carnivores, and sometimes they are omnivores as well. Tertiary, sometimes omnivores, many times carnivores, and again an omnivore eats both plants and animals. Detritivores eat detritus, and that's waste and skin and feces, like snails, crabs, and clams and worms. And saprotrophs are decomposers like bacteria. Scavengers, those are vultures, and they feed on dead things as well. Kind of smart. They don't expend a lot of energy in the hunt. Like a hawk will hunt, or a lion will hunt. Vultures just wait for something to die, and then they eat it. So they're kind of lazy, if you think about it. Another scavenger, although he's not completely a scavenger, is a hyena. Hyenas will eat dead organisms too, but they also will hunt some. When we look at how energy moves. We use a pyramid as the example of movement. A pyramid, think of the shape of a pyramid. What is the relationship of the top to the bottom? The top is smaller. It shows that energy moves through the ecosystem and energy gets less as it reaches the top. So the top is smaller than the bottom. So we have two different types of pyramids here. One is the pyramid of numbers and one is biomass. So the pyramid of numbers actually is the actual number of that organism it takes to feed that next level. So let's look at this. Go down to the producer. It takes 10,000 blades of grass to feed 10 mice that feeds one hawk. So in essence, 10,000 blades of grass feed one hawk. That's what that tells you. And those are numbers. Look at the biomass. Biomass is usually represented in grams per meter squared. Biomass says there's 10 grams, or 10,000 grams, 10,000 grams per meter squared of grass. And this will feed 1,000 grams per meter squared of grasshoppers. Not 10,000 grasshoppers, or 1,000 grasshoppers, sorry, but 10,000 grams. So that's weighing the grasshopper. And biomass is devoid of water. So this is actually the dry matter that you're getting here. Then 100 frogs can be fed and 10 snakes. Look at the 10,000, the 1,000, the 100, and the 10. It's every time it's 10%. 10%. This is showing the 10% rule. So metabolism of each individual yields 90% of the energy gleaned from the level below to that next organism. 90% is lost. So only 10% is available. So of the 10,000 grams in the grass, there's only 1,000 grams sequestered in the bug, 100 grams sequestered in the frog, 10 grams sequestered in the snake. This is why a food chain cannot be very long, because at every avenue you're losing 90% of the energy every time. So eventually when you get up to those top consumers, energy is very, very limited for their use. This is showing it in pyramid form, and instead of showing it in grams, we're actually going to show it in calories. So, and it can be done this way too. And this is, again, the 10% rule. At every exchange of energy, there is heat loss of 90%, so only 10% of that energy moves to the next level. So basically 1,000 kilocalories of grass can feed 1 kilocalorie, or provides 1 kilocalorie of food for the owl as it goes through the transfers. And again, you're seeing the 10% rule. And 10% is the availability of energy. Ecosystem productivity. We're looking at two different ecosystems, a desert, temperate forest, and these are all trees, and this is the fall. That's why they're different colors. You got a nice river running through here, somewhere in Tennessee maybe. And what we see here with ecosystem productivity is that there's a norm for each ecosystem. And the amount of productivity, or of producers, the biomass that they create per meter squared is different. Okay? Limiting factor here in the desert. What's the limiting factor in the desert? Water, right? And so you're not going to have as many plants per meter squared. So possibly you have 100 grams per meter squared of biomass that organisms can utilize. Where here, very dense forest, you have 1,500 grams per meter squared of biomass. Which one can hold more organisms, or possibly even be more biodiverse? The temperate forest is going to be more biodiverse and have higher population numbers than the desert does. Very good reason for that. There's more productivity, so it can support, it has a larger base than the desert does. We're going to pause here and, well, stop this video here, and the next part of this will be in section 3 of chapter 3.